Here we'll look at how to do quantitative calculations for strong acids and strong hydroxide bases. For 5 of the 6 strong acids we'll consider, it's relatively easy to get the pH or hydronium ion calculation at equilibrium, and that is because by definition strong acids about 100% ionized. Remember that strong acids are molecules, they are covalently bonded, and when they're put into water there will be a chemical reaction. The covalent bond between the H and the, in this case, Cl, will break. 100% of them will, approximately, at equilibrium. So the 2 electrons shared between the H and the Cl will stay with the chlorine, and the H plus ion will form a covalent bond with the water, thus generating the hydronium ion. So you get H3O plus and the chloride approximately 100% at equilibrium. So not showing the water in the above equations, we just abbreviate H3O plus as H plus. On the other hand, for the strong acids, those are already ionic compounds. They're ions to begin with, so they do not ionize. They're ions already, so they can't re-become ions. They simply, when they crash into water molecules with enough force and energy, they dissociate from the lattice. So these solid ionic compounds will form solutions of aqueous ions. For each formula unit of, say, lithium hydroxide, one single lithium ion is dissolved and surrounded by water, so you get one aqueous lithium ion and one aqueous hydroxide ion per formula unit that is dissociated from that lattice. And you can just scale that up to the mole level. For each mole of lithium hydroxide formula units dissociated from the lattice, you get 1 mole of lithium ions aqueous in solution and 1 mole of hydroxide ions aqueous in solution. There are 3 soluble and therefore strong bases that are dihydroxy bases. For each mole of formula units, let's say of calcium hydroxide, you get 1 mole of aqueous calcium ions, but you get twice as many, or 2 moles of aqueous hydroxide ions. So naturally that's going to have an effect on the pH calculation for a given number of moles of calcium hydroxide formula units dissolved per liter of solution. So now let's look at an example. What is the pH of a 7.20 times 10 to the minus 3 molar solution of any strong acid except for sulfuric acid? These acid molecules 100% ionize about at equilibrium, so therefore the concentration of the acid is going to be the concentration of the hydrogen ion or hydronium ion, as well as the concentration of whatever anions form from the acid. So we know that at equilibrium the H plus concentration is going to be almost exactly 0.00720 molar, and from that you can directly get the pH. Since this is 7.20 times 10 to the minus 3 molar in H plus, we know that without even using a calculator, 7 goes to about 2, the 3 turns into a 2, so very closely that's going to be a pH of 2.2. You can show this in an organizer. You have the HCl molecules undissociated. They'll change in a 1:1:1 ratio with the H plus ions, really hydronium ions that form, and the chloride ions that form. So you'll have about 0 molar HCl as molecules at equilibrium, and you're going to have, because x would have to be 0.00720 if taking away 1x is going to leave you with 0. So we know that this is going to be negative 0.00720. So that's going to give us, at equilibrium, exactly what we saw to begin with, 0.00720 molar H plus ion concentration, and that leads right to that calculation. Now here's an example of when you actually would need an organizer to not reach a misleading and wrong answer. Can you just take the molarity of any strong acid and just take the negative log of that number and get the pH? Well, even though this would be literally a crazy case, having a solution of a strong acid, say HCl, that is so unbelievably dilute that it's 100 millionth molar, it does show that the organizer can come in handy if you ever see such a crazy situation. So here we're starting with 10 to the minus 8 molar hydrochloric acid. It's a strong acid, so it 100% ionizes. But here, this number is so incredibly small that the initial amount of H plus in solution is actually 10 times greater just from water, just from the autoionization of water, and there's no chloride yet. So I almost always put 0 as the initial H plus concentration, because 10 to the minus 7 molar H plus from water is generally negligible for any normal problem. But here's one exceptional case where it would not be. So all of the HCl ionizes, as we see from the change line here. So that forms H plus and Cl minus aqueous, and we're left with approximately no HCl molecules in solution. Now we have, at equilibrium, 10 to the minus 7 plus 10 to the minus 8 molar, which if you wrote that out, that would be quite a lot of zeros, so I'll just leave it like that. And the chloride is 10 to the minus 8 molar. To get the pH, you take the negative log of the H plus concentration at equilibrium, and that's by definition the pH, so the negative log of that sum is 6.96. So it's practically neutral at such a low molarity of the acid, but it's very, very slightly on the acidic side. Had you just taken the negative log of 10 to the minus 8, you would have had a basic pH, and that's not possible for an aqueous acid solution. Now let's take a look at hydroxide bases. Again, these are ionic compounds. We'll look at a monohydroxy base, such as lithium hydroxide, versus a dihydroxy base, where, as you can see from this little section of the lattice, the ionic lattice of this ionic compound, this hydroxide base, that for every strontium cation that dissociates from the lattice, that becomes aqueous strontium cation, you get 2 hydroxide ions dissociated that become aqueous hydroxide. So if I use the term 0.0347 molar, I'm talking about 0.0347 moles of strontium hydroxide, formula units dissolved. So they're no longer in the lattice. They're dissolved, they're dissociated. So we're only artificially in our mind calling them formula units as if they were stuck together. And that is per liter of solution formed. And the same situation with 0.0347 molar lithium hydroxide, it's again 0.0347 moles of lithium hydroxide formula units dissolved per liter of solution formed. And that doesn't have to be a saturated solution necessarily. It could be. If you tried to dissolve more than the amount of solid that could dissolve at the saturation point, any excess lithium hydroxide or strontium hydroxide would just go to the bottom of the beaker eventually. Alright, so for the organizers, ICE, initial, change, and at equilibrium, you can just X out the solid line. The concentration of those solid ionic compounds won't change. The key line is the change line, which you can tell from the stoichiometry is 1 to 1, 1x to 1x for lithium and hydroxide, but 1x to 2x for strontium and hydroxide, just by nature of the dissolving process and the stoichiometry there. So since we have 0.0347 moles of formula units per liter of solution, that's going to give rise to 0.0347 molar lithium at equilibrium and the same concentration for the hydroxide. Whereas for the strontium hydroxide, you get twice the value of the strontium cation aqueous concentration than you do for the hydroxide concentration. So we're interested in pH, from POH we can get the pH. So we'll approximate these without a calculator. For the hydroxide, from lithium hydroxide, we have 3.47 times 10 to the minus 2 molar. That's going to give us a pOH of 1. That comes from the negative 2. And if this were 3 times 10 to the minus 2, this would be 1.5. It's a little more than 3 times 10 to the minus 2, but really not that much more. So to two significant figures, we'll call it 1.5. And that means the pH would be, make that P a little bit smaller, pH will be 14 minus the pOH, which is going to be 12.5. For the same concentration of formula units of the strontium hydroxide, we have a hydroxide concentration of 6.94 times 10 to the minus 2. That's almost 7 times 10 to the minus 2. That gives us a pOH. Remember, the 7 turns into a 0.2. So that's going to give us a pH of 14 minus 1.2, which is 12.8. So it doesn't seem like a large difference in pH, but it is 0.3 pH units, and you know that a difference of 1 pH unit is a 10-fold difference in concentration of hydroxide. So it would be somewhat significant. And as expected, we get a higher pH given the same concentration of formula units dissolved per liter of solution from the dihydroxy base as compared to the monohydroxy strong base. One more example. What about aluminum hydroxide, a trihydroxy base? However, aluminum hydroxide is an insoluble base. Now, there's no such thing as a 100% insoluble anything, so forming a saturated solution of aluminum hydroxide, in other words, you dissolve as much of the solid as possible until you see excess solid undissolved, and then you filter out the excess solid, and you'll have a relatively low concentration of hydroxide ions even at the saturation point. So if you try to dissolve 0.0347 moles of aluminum hydroxide per liter of solution, you just would not be able to do so. So this is not really possible. You would have to be given some kind of solubility product constant value for aluminum hydroxide, which will give you a quantitative measure of just how much aluminum hydroxide solid will dissolve per liter of solution. For now, we'll just take a qualitative guess. A good guess would be that the molarity of hydroxide, even from a saturated solution of aluminum hydroxide, is relatively low. We'll say around a millionth molar. That could be wrong, could be right, but it's a pretty good guess. So the pH would be slightly above 7. It would be 7 just from the hydroxide contribution from water. So you get a little bit more at the saturation point of this dissolving this relatively insoluble solid ionic compound. So maybe around 8 at the saturation point would be a good guess. Again, we can get a much more accurate quantitative calculation once you're given a KSP value and you understand sparingly soluble ionic compound equilibria.